today.
Okay, so hello. This is Chris Friendly. I'm going to talk about TensorFlow. And welcome.
Yeah, this is a 3.5 hour, 4 hour, yes, I feel like you, right? It's like a 4 hour talk that I'm doing in 30 minutes. So yeah, so Chris Fregley, thank you for having me. Super excited. I'm based in San Francisco, started this company Pipeline.io about 9 months ago. We spent a lot of time talking about GPUs and all kinds of fun stuff. So let me see here. This is introductions. Yeah, former Netflix, former Databricks, the Spark people. I have this advanced Spark TensorFlow meetup. I want to talk about this stuff real quick just because there's way more resources right, that are out there. We have a London chapter. There's actually upcoming events. We've got a meetup coming up over at thehotels.com. Like they're one of my users for Pipeline.io. So posting, I think it's the 23rd. Yeah, just got the email today. It'll be an expanded version of this. You'll have GPUs. I found one problem with these GPU instances. Oh yeah, and there's this workshop too that I'm doing coming up. Yeah, you guys, software engineers, data scientists, hopefully know a thing or two about TensorFlow. We're not going to get through like nearly like any of this material, but I want to give you guys, since I already spun them up, that we're all going to get a GPU, and this is the Google GPUs. Yeah, so not the Amazon ones, but it's these new Google ones that you can attach to your CPU. What I realized about 20 minutes ago when I was sitting in the session right before is that the instances, the CPU instances that Google gives me in this region, right, like don't have right, like AVX2 and all that kind of stuff on it. So how'd I spun them up? Oh, the short of it is that things like TensorBoard aren't going to work. I don't think any of the TensorFlow things will actually work. But like we can talk through them, and since I already spun them up, you can kind of poke around. So yeah, grab your IP address from, it's just a simple REST API, and then go to that and just kind of see how far you can get. The username is root. I'm going to tear these things down so fast, you guys won't even be out the door yet. They're going to be done because I'm paying for these myself. So yeah, so right when like 30 minutes are over, yeah, don't expect them to be there anymore. Just use root. Yeah, the title of the talk is, I guess, right, like high performance, like TensorFlow. So what I'm going to do is kind of blaze through some of these slides, since these notebooks aren't really going to like get too far. Things like half precision, things like this, right, that are now available on the like P100. This is the ability to actually cram in two, right, like floating point 16s into one like floating point 32 lane on the GPUs. Right, like, has anyone done any CUDA programming? Sure, yeah, a couple people. Is it as barbaric as, I mean, yeah, do you guys find it barbaric? Is it just C, I guess, is barbaric? Maybe, I forgot. What's funny, I make this joke, is that the NVIDIA guys give us great tools to debug and profile our shitty code that we write in CUDA, right? Like where they could just make it less easy to write shitty code if they gave us, right? But like the code's been there for a while. Yeah, there's like Eclipse plugins and the NVIDIA profilers and things like that. But if you're doing, right, like hardcore CUDA programming, right, like you really have to know your hardware specs and what you're dealing with, right? So one thing that we will be able to do here is actually do the first part, which is just CUDA coding. So yeah, we're gonna demonstrate CUDA streams. CUDA streams let you do, right, like async sort of overlapping. And so this is really important when you start dealing with TensorFlow queues, right? Yeah, so you're talking about at the very end of the talk. These queues are super important. If you're using feed-dict right now, you're just stop. Just stop doing it. It's like using collect in Spark, right? Like, it's in all the examples, but if you start typing it, just stop. Yeah, so start using queues, especially for GPUs. You want to saturate these GPUs. Yeah, these queues give you the ability to actually pull in parallel. And because of these streams, right, like you can actually get that data to the GPU and it's gonna sit there waiting. And so right when it's done, right, like with the previous batch, it'll start on that like next batch that's sitting there waiting. So if you're using feed-dict, it has to get serialized, you know, especially from Python to C. It's right, like synchronous kind of single-threaded. I think that they're working on feed-dict is what someone told me just, I think, yesterday. The TensorFlow engineers, because so many people don't even really know about queues, and queues are, you know, like a little bit wonky to code. They're trying to make the actual just normal feed-dict a lot more parallel and things like that. So yeah, so all of these, this is all open source. Yeah, these notebooks are all out there. The same Docker image that like we're all using is out there as well too, so you can just navigate to this. But if you guys have your instance up, yeah, so we can actually go. Let's see here if I can. Actually, yes, I'm going to skip right like the CUDA stuff, but it like basically shows you if you do it the old crappy way without streams, and then if you do it the new nice way with streams, yeah, right, like you get some like performance gains there. It's basically trying to move memory in parallel, right, in and out of that GPU. Let's see, training devices. Yeah, keep an eye out for these new XLA CPU device, and I like the XLA GPU. I'm going to talk a little bit about the XLA stuff. This is the accelerated linear algebra framework, right, by by Google. And there's two big projects on top of it. There's the JIT compiler, and there's the actual AOT compiler, right? And so both of these super important for rally performance. And what you could do is during training is that you can actually, instead of assigning it to a CPU or GPU, right, you'd actually say assign it to an XLA underscore CPU or GPU. And then that's a hint to the TensorFlow compiler to right, like try to like JIT these things together. You know, fusing operators, that kind of stuff. TensorBoard, I believe, is busted because of the like AVX thing. Yeah, so what happened was, because this is a performance class, I turned on all the flags that like TensorFlow has, right? So I turned on all the Intel optimizations, all the GPU optimizations, everything possible. And yeah, so Amazon in some regions really doesn't support it. I found all those issues, but yeah, not until this is my third or fourth region with Google, and yeah, this is the one giving me problems. So yeah, maybe get on Google's case for that. Yeah, I believe someone asked yesterday in like your talk about right, like HDFS, if you're trying to get to right, like your existing HDFS data. So there's this it's a top level project off of TensorFlow. It's called Ecosystem, and yeah, this has things for like Kubernetes, HDFS, Spark integration, Mesos, Docker. Yeah, so no more feed-dict. Just forget about that. Use queues. Like the code's a little bit wonkier, but you're rather definitely going to saturate CPU and like GPUs. Yeah, so also these queues aren't just queues, right? Like they're not just like sitting there with data. They're actually really capable of doing like pre-processing. So, you know, picture this pipeline where you have to like crop images and you want to, you know, like skew them and kind of like show the network different views of a specific image, right? These things can be handled by the queues themselves. And there's like shuffling queues that'll just randomly shuffle. Yeah, so this is stuff that like you don't have to code yourself. Slides on, yes, I'm gonna post these also. They're not in the current Rally GPU ML repo, but they will be probably on the flight back tomorrow. There's a notebook. Did this notebook work? I'm gonna try to get this one to work. P2 and P2. TensorFlow model, I'm gonna assume you guys know this stuff. All right, do you guys know about the debugger? Yeah, the TensorFlow debugger. This is pretty snazzy. You wrap your TensorFlow session in this debugger session, and it gives you the ability to actually step through and see tensors. And it like looks like this like horrible command line thing, right? But you can actually like use your mouse and kind of click back and forth, and it's kind of fun. It's like the craziest like ASCII command line tool. There's more of these coming out of like Google too that like you start seeing kind of flow through like pull requests and things like that. So especially for like the XLA stuff, there's like a few things that they haven't like released yet that I've been hearing about. All right, so distributed TensorFlow. The whole reason TensorFlow is popular, at least in my opinion, is the distributed nature of it, right? So it's just like anything. Like when you first get your Spark cluster, you first start working with Spark single node, and then like, all right, this is great, but now I have a big data set. Now what do I do? Yeah, so Google doesn't do anything single node, obviously, right? The problem with distributed TensorFlow is that it's not very well documented. It's been changing, right, like quite a bit. There's huge API changes that are even coming in right, like 1.1 or 1.2. With any distributed system, right, there's failures, there's different types of node failures, there's certain, right, like nodes that are more right, like specialized, and like the master and the chief and things like that. And right, like the term zookeeper starts popping up and everyone gets all freaked out, right? But so yeah, oh yeah, this is actually single node multi-GPU. Just real quick on this, the CPU sort of acts like a parameter server, right? So this is one node, but you kind of, right, like give the CPU sort of the dumbest task, which is just store these values, then pass, right, like the more complex matrix multiplies, right, like to the GPU, to, right, like each GPU, and then they send it back, and then, right, yeah, so that CPU just does like an average or a, sum, something like that, and then, right, like rebroadcasts out those gradients. But the actual GPUs themselves are what's doing the, right, like the complex stuff. So now this is more general. This is across nodes. The left here is single node. If you do switch then, that same code, you would switch over to multi-node. Yeah, so TensorFlow starts to add these send and receive things, right? Yeah, so you don't have to worry about those yourself. But yeah, those become nodes inside of your graph and right, like have right, like that responsibility using gRPC. And then this is a parameter server here. So right, like similar to the CPU thing, except this is a cluster of servers whose job it is to just maintain these values and to just do the averaging for the gradients and then broadcast that, right? There's synchronous, right? There's asynchronous, where certain, right, like nodes could be operating on older values because they're slower, like things like that. So yeah, you have to like sort of make trade-offs there. There's the synchronous, asynchronous. Yeah, so there's data parallel versus model parallel. The one that we're probably most familiar with is data parallel. And so that's how Spark works, right? You take a data set, you split it up, and each node has the same graph, the same model. And it's just gonna, right, like take the data that it sees, hopefully shuffled. It's going to then calculate the gradient and then send it back. For the model parallel, this is, super large models that won't fit inside of one GPU, right, like memory, right? Because these are 12 gig or possibly 16 gig, something like that. So for that, like you can only put parts of that same model, right? Like you have to split the model up. And then each worker then sees all the data, but has just one part of the model. Yeah, so the XLA, it's pretty experimental. Yeah, even when, right, like TensorFlow is working for these demos, things get a little wonky in this area. There's ways to work around it, but let's see. Yeah, the whole goal here is, right, like to basically fuse things together, fuse operators, right, like similar to Spark, right? Like I talk a lot about Spark as Databricks and right, like my experiences there and just watching that project evolve. But think of like the ability to combine MapReduce. So like, right, like when Spark first came out, it was better than Hadoop because it would take the map, it would take the filter, it would, right, like put them on the same node, right, like possibly, and not have to actually write data to disk and pull it up and do all the intermediate things like that. In Spark 2.0, they actually break apart, right, the map and the filter, and they physically create one Java function, right? There's this project called Janino that can take a string and then actually compile it on the fly. And so that becomes now your new virtual, or right, like this new function. It's going to cache, right, that like class file or that function or whatever, so that it's not constantly being rebuilt. But yeah, so that way you just pull in memory once, and then you can just kind of rip through all the data. And so you're not, right, like putting data back, into RAM and then point it back. So it sort of builds on top of like the same pattern of not having to go to disk. So if you're not pulling from like main memory, that data is in the registers. This concept of the HLO, so think, yeah, this is, yeah, so terms right, like LLVM should sound familiar, where it's sort of an intermediate representation, right? So the kind of simplest way to think of it is like a logical plan, right, that gets converted into a physical plan that's targeted to the actual hardware that your queries run on, right? Right now there's GPU NVPTX support. That's the instruction set for the NVIDIA GPUs. ARM, of course, the Android devices, and then x86, the CPU instruction sets. And so there's this whole host of, so for the XLA stuff, there's, I think I have a reference in the actual like notebook on this that has all of the operations, right? And it's ways to fuse things together and like all the fancy stuff that's going on. So just-in-time compiler builds on top of the XLA framework. So this is during training time, for example. This is similar to what I just described with Spark. It's going to unroll loops and constant folding and all the classic. So yeah, this is, yeah, here's an example of when you place just a simple, squaring, and you, yeah, so this is the actual assembly that was generated. It's much tighter than if you didn't do that. And then here's a like visualization. There's a lab on this out there as well too. This is the snippet of code that actually creates these things. And then you could use like the Google web tracing framework to actually render it. So this code puts it into a format that is this timeline thing. So you can actually see here, there's a bunch of operations, right, that all get like jittered into one XLA plot. So this is huge, right? This is huge performance gains. There's another visualization. This is all like tooling that's available. If you look at this notebook, just kind of look at the comments, whatever you'll see. From this point on, we're in, yeah, how much time do I have? I have like 2 seconds. Oh, I do. Oh, shit. Slow it down. So from this point on, this is going to be like mostly inference talk. So this is like the prediction side of things. So yeah, these are optimizations now. That model has been trained, and yeah, so there's certain things that like we can do to actually make the prediction side faster. So this is where the AOT side of this comes into play. So for example, so picture this model has been built, and now we want to just try to minimize the actual runtime that gets pulled in, right? So you can pass into the XLA framework, there's this tf compile command, and tell it like where to start with your node, which is typically like the input that you're feeding in, right? Because you're predicting. And then you give it the fetch side of things, which is the actual prediction. And so TensorFlow can go through and figure out what's the bare minimum, right? Yeah, so from the actual TensorFlow runtime, which kernels do I need, right, to actually pull in? And that's all it's going to pull in, right? And now the TensorFlow runtime itself is not that large. I think it's 20 meg, 30 meg. But if you can shrink it down to, like 600K, which is one example, from, I think it was 1.5 meg model, plus your 30 meg runtime. But they, yes, with this TF compile, you can actually strip all that away and really just have a final binary that's 600. Okay, so yeah, this gets packaged up as a CC library. It's got a header file, object file. You can link to it. And this is commonly used on these embedded devices, things like that. Currently, there is no GPU support. This is basically because a lot of these small devices don't have GPUs, so there hasn't been a lot of like effort put into that. Okay, so the graph transform tool is pretty sweet. This thing, so during training, right, there's all these nodes, right? There's the send receive nodes that I showed. There's nodes that are logging things that are like for TensorBoard, right? Because like TensorBoard, yeah, so periodically, like you're writing out how's my loss function doing here, compared to my it's like test validation, like that kind of stuff. So yes, all of those things can get stripped out, right? Like there's, yeah, so that's pretty obvious. There's certain things like dropout, right? So dropout, so this is only there at training time. Now, some people might be thinking, well, when you do the inference side of things, don't you have to adjust for that? And yes, you do. And so TensorFlow does this trick where it will actually boost, right? So the final value that gets frozen, right, like into this model has boosted values on the non-dropout, right, like connections, right? So normally you would think of it as those connections are dropped and then everything stays the same, but yeah, TensorFlow boosts it so that you don't have to maintain which ones were dropped out. Yeah, because that would be way too much overhead. So yeah, keep an eye on that. There's right, like the classic dropout paper does not talk about that, and so that's why like you have to kind of combine that with some of the documentation that's in like TensorFlow, which is confusing until you realize that trick that they're doing with the boosting on the other sides of those dropped out connections. Yeah, so things like batch normalization, you should always be using batch normalization, by the way, because we're doing mini batch gradient descent here, right? Like we're not training on each piece of data because that's too small. And like we're not training on the entire data set because that's too big, right? So we're doing mini batches. Because these things are getting shuffled randomly, they could be all over the place, right? So one problem, right, that these networks have is that like they have to see this distribution, which could be wildly, right, like changing, depending on. And so batch normalization helps shrink that down, helps like converge quicker and train faster, and there's basically no reason to not use it. So when you're done, what you can do is actually burn those weights in, right, those like pre-calculated weights that were learned from this batch normalization process through the training process. And so like you don't actually have to do those matrix multiplies again, you can just calculate them once and then burn them into the final model for the inference side. Things like quantization, this is pretty cool. There's a lot of examples on this. So Google bought this guy's company, Pete Worden, who I think is actually based, or, yeah, was based here, probably still is based here. Yeah, he has, right, like, it's probably the best blog post on this kind of stuff. He's the guy that actually built the graph transform tool. When he came to Google, he had kind of this like loose collection of things, and like people started to write their own post-training optimizations, and so he decided to go make this framework called the graph transform tool that like you can then hook into. And but yeah, weight quantization. This is yeah. So once you've actually trained the model, right, like now you know all the weights, and like you can kind of fit them all in. So right, like you're going to lose precision here, of course, but I mean, it like greatly reduces the size. In fact, the notebooks actually, we take a 32K model, just a simple model, linear regression. We run the 8-bit quantization, and it goes down to, I think, like 13K. And that's just a simple, just like a pass-through boom. It's basically taking all the floats that it sees and slotting them into these 256 8-bit slots, right? And because, you know, this whole deep learning stuff's all fuzzy anyway, it still works out, right? Well, that's the big. There's, yes, activation, quantization. This is not as easy as doing that because those values aren't known, right? Like the activation side of things, the input, right? This is like dependent on the inputs. So when you're trying to quantize this part of it, what you need to do is actually calibrate, pull some data that's like most representative of the data set. This is, yeah, that's the tricky part right there. It's not a lot of data though. And so you pass it through and now, right, like you can quantize based on like the values that it sees from like the inputs and then like the output like activation. Here's a quick visual of, so this is, yeah, so it's just finding min and max and then smashing them into the like negative 128 to positive 127. Batch normalization, yeah, always use it. Yeah, and so the graph transform tool, this is a first class transformation here. It takes the final mean, final variance, and it sticks it in and like pre-calculates all of the weights here. Okay. We have a couple minutes left. Yeah, so no one really ever gets around to talking about TensorFlow serving because it's always the last part of, and I thought about actually like doing it first, but yeah, we would have missed all that stuff with like the graph transforms and things like that. But the key takeaway here is to use like request batching. And so I think I have an image of it here. See if there's anything on this slide. Yes, one thing about TensorFlow serving that changed like dramatically with like TensorFlow 1.0 is the actual model format. So before, you know, there was like this export format and that, you know, had these checkpoint files and had files everywhere and, you know, dot meta files and just seemed like an endless. And yeah, so now for the serving side of things, and this is starting to propagate through to the training stuff as well, you actually like save the model. And it's just called, I think it's just called savemodel.pb, which is really protobuf. Oh, yeah, so I should mention too that like TensorFlow stores the graph separately because that's static. That's actual architecture, right? That's your DAG. And then has the variables separate because you can pull those variables in again, those weights, and start to train again, right? Which is something that was discussed yesterday as well. So yeah, that pattern still, what happens, yeah, okay. There's a lot of really cool TensorFlow serving features. So when I first started Pipeline, we had thought about doing our own TensorFlow serving engine, right? And just kind of bypassing Google. Oh yeah, like they're just throwing something out there just to keep, you know, people happy or whatever. And this project has lagged behind TensorFlow itself. It's always kind of a question if you do get the new TensorFlow, is TensorFlow serving still going to compile, you know, things like that. They've gotten a tiny bit better. But if you go look at the stars, for example, I think there's only like 15 or 2,000 stars on TensorFlow serving. There's like, I just checked, there's like 56,000 on like TensorFlow. So, but like to me, this is the most interesting, right? Because think of how many people use TensorFlow serving. What was it? Oh, 5 minutes. It's right, like all of the users that are using like, right, like your system. So whereas TensorFlow training side of things is just it's just the data scientists, it's just the actual people in your group. So in terms of right, like Big O, right, like this stuff's a lot more interesting, at least to me anyway. So yeah, I've combined some of my Netflix experience, you know, with like circuit breakers and fallbacks and all this kind of stuff. But yeah, so back to this TensorFlow serving stuff with Google, they keep announcing more and more things, and I keep seeing right, these like pull requests that come in that are like 900 files, and it's like, it's, you know, it's just got one comment, right? And it says like, we're finally making this public, and it's this huge experimentation framework and, you know, A/B testing. And I'm like, all right, well, if I had spent the last 6 months building that would have been a complete waste of time. So you see, you know, 1 or 2 of those, and you're just like, all right, I'm just gonna, you know, wrap this thing, figure out how to really use it. So fortunately, they've split it out. I'm not sure if I got to that slide yet. There's one server.core, right, like it's like C++ file that you can include, and then you gain access to all of the games. But that just changed in the last few months. Prediction service. The original prediction service was just predict. You passed in tensors, you got out tensors. They've now added classify. They've added regression. What you're starting to see is CloudML, which is their product, right? Their right, like service that is using like TensorFlow, right? Like features come out on that shortly after you see them kind of right, like pop up in the open source stuff, right? So they make API changes, huge API changes to TensorFlow serving and huge experimentation frameworks because they're using it, right? And yeah, so they want you to start using these example classes. For example, this is like the worst name for it, but yeah, so I guess that's what they're called, right? Examples. If you like speak about it casually, people are like, oh, it's example code. I can pay attention, but this is actually a super core right, like component to the new like TensorFlow stuff here. So yeah, so they added classify, they added like the regression stuff, and then of course these things show up as first class citizens within CloudML, which is not surprising, but just kind of funny to note. The other thing that changed, there's signature defs. So one big thing here is that when you used to use TensorFlow serving, you had to know the actual physical name of the input node, of the feed node, right? And that could be named anything. It could be first named anything by the actual person creating, right, that graph that's actually training the graph. But then it could get munged and have a :0 or a :1, depending on if, if there's other variable names that just happen to be in scope at the time. So it was always kind of a crapshoot, like, did I get the right name for the inputs? And so now there's this sort of logical thing, right, that doesn't change. And when someone hands you this model, they keep the logical one the same, hopefully. And they've done the mapping on the inside. Yeah, so there's this method, build tensor info, that actually takes, right, like whatever name it is at that point, right, like you never have to know. Yeah, multi-headed inference, this was another thing that we had talked about a little bit, yeah, sort of internally, and then all of a sudden, boom, yeah, Google has it. So this is one pass in, and you could do both regression and both classification, and that data comes in just once, and you save a lot. Here's that server core that you can import if you want to do your own. Yeah, the request batching. So this, yes, we use this quite a bit at like Netflix when we have so much data coming in, so many people asking, for the metadata for some movie or some TV show. And so picture, these are separate requests coming in, right? Separate requests. If you can kind of wait, 10 milliseconds, right? That's the batch timeout, right? And then just batch them all up. You can pad with zeros. You can really do that, but you sort of logically build up a big matrix from these, smaller matrix multiplies. Make one big matrix multiply, pass it to the GPU, pull it back, and because if you know the offsets, it's the same result, and that goes back to that client, which could be anywhere in the world, and that goes back to the other. So it's an obvious trade-off between throughput and latency. Huge performance gains there. If you have low throughput, don't use it, because you'll probably always have a 10 millisecond pause, and that's it. Fastest I've ever gotten through that. Oh. Any questions? Do we have time for questions? Was that interesting? Yes, I have a question. Was it interesting? Was it, was it what you were expecting?
Yeah.
Yeah. Yeah, the question is, so this would be back to the AOT stuff, probably, right? The TF compile, where the best blog to look for that stuff is that guy, Pete Warden, W-A-R-D-E-N. I think it's just Pete. It's like PeteWarden.com, and he has all the specs in there. Yeah. The big thing there, too, is the size, right? Just the pure size of you're stripping out nodes, of course, so the forward prop, right? Because like when you're training, it's forward prop, then back prop, forward prop, and then back prop. I think I was doing that, you're right. But when it's on like the inference prediction side, it's just forward prop. So you want to reduce the number of, yeah. That's a good question. Yeah. 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 Yeah, I mean, it's the classic. So I think it's the classic question of how do you know what is representative, and so what you would do is not quantize, right? Just just take the slow model, and it's and just basically validate on the so compare the slow model to this newly quantized model that's been recalibrated, and just keep an eye on that, right? Because the accuracy of the old model that has not been quantized, and then you go and then recalibrate it and then quantize it and just compare the accuracy. If it's wildly off, then you've chosen a data set that isn't able to generalize, and it's chosen these normalized weights that are way off, or these activations. Yeah, I mean, yeah, I don't have any more than that. Just it's really knowing your domain and that kind of thing, right?
Another question? Anyone?
Yeah, man. Question is, if I have a Spark project, how do is there any benefit to moving to TensorFlow, right? I mean, yeah, this is every single person that I talk to is like going through this exact same thing, right? And the big barrier obviously is there's not a whole lot of real world examples of TensorFlow, that are out there. Like we're starting to see more, and like Google certainly did a really good job by giving us examples, and like complex examples too, right? Like the MNIST and right, like CFAR and all that stuff, not just kind of toy examples. But I mean, yeah, I always just kind of recommend use Spark for ETL, man, and get it into HDFS, get it anywhere, and then rip through it with TensorFlow. Yeah, thanks. I can't believe I went through like 100 slides. Did it come through okay?
Yes, came through perfect, yeah.
Still on. MacBook's about to blow up. The fans like going crazy.
I was trying to figure everything on the train. Yeah. Until I started to talk to the people.
Oh, man, it's hot over here too. I thought it was just hot. It's hot everywhere in this room, not just up by. Sorry.
Hello? Can I please ask people to talk about doing the class? So the next speaker is INFERENCE. with a background in pharmacology, and he's working in a biotech company. And he's going to talk about the analyzing the electrocardiogram and the downloading. Welcome. Please welcome him.
Hello everyone. So I'm Emily. You've known me already. This is me. So my background academically is in pharmacology. My bachelor's was pharmacology and genomics, and I did my PhD in pharmacology, of which I've mostly been involved in preclinical and clinical validation of drugs. So that involves cells, animals, and humans. And I've worked with them all. And the talk I'm giving today is about analysing normal clinical validation or abnormal clinical validation. You have to do cardiotoxicological studies to check that the effect of the drug doesn't cause adverse effects on the autonomic nervous system, of which we use the UCG as a reference point for that. UCG is a famous waveform. If you ever see a medical company and they're using it on their logo, they probably use UCG. It's a really nice signal. All